Hey everyone, and welcome. So today we're diving into a topic that, let's be honest, can feel like a totally impossible puzzle: balancing chemical equations. For so many of us, it's this frustrating mix of just guesswork and crossing your fingers. But what if I told you it's not about luck at all? It's actually all about logic. And by the end of this, you're going to have the key to unlock any equation they can throw at you. Let's kick things off with a feeling that is probably way too familiar. This quote from Mind Matters Pedagogy. Wow. Yeah, this probably hits close to home for anyone who's ever sat in a chemistry class. It just perfectly captures that feeling of being completely stuck. You're just throwing numbers at a problem, hoping anything sticks. So, does it? Have you ever been that person just staring blankly at the page with no idea where to even start? Trust me, you are not alone. It's a universal struggle. But the good news is, the reason for that struggle is often totally misunderstood. You see, research shows that the real stumbling block isn't the final act of balancing itself. Nope. It actually comes down to four key misunderstandings about the very language of chemistry. If we can fix these foundational issues, the balancing part, it pretty much takes care of itself. Okay, so mistake number one is not getting that a chemical formula is a fixed identity. Like, look here, on the left, we've got H2O, water, good stuff. But on the right, H2O2. Just by changing that tiny little number, the subscript, we've gone from the stuff of life to hydrogen peroxide. So changing a subscript doesn't balance your equation, it illegally creates a whole new substance. Mistake number two is all about ionic compounds. And honestly, there's a fantastic analogy for this one. Think of it like splitting the bill at a restaurant. If sodium, with its +1 charge, goes out with oxygen, who's got a -2 charge, well, someone's going to come up short. To make it fair, sodium needs to bring a friend. And that's why the formula is Na2O. The charges have to balance out to 0. It's not just about listing the elements. It's about making sure the whole transaction is neutral. All right, on to mistake number 3, messing with polyatomic ions. A great way to think of these is like they're tiny gangs. Something like nitrate, NO3, they roll together. They react as a single unit. And if you need more than one of them in a formula, you don't break up the gang. No way. You put them in brackets, like MgNO3-2, to show you've got 2 whole nitrate units. You gotta treat the gang with respect, and they won't cause you any trouble. And this brings us to mistake number 4, which is the big one. This clarifies the entire game. Think of this subscript, that little number, as the molecule's DNA. It defines what it is. You can't change it, ever. But the coefficient, the big number out front, that's just the quantity. It's how many of that molecule you have. That is the only thing you are allowed to change when you balance. So it all boils down to this. A molecule's identity, its DNA, is sacred. The quantity, totally negotiable. That's the whole game. So, once you've got those fundamentals down, what about those truly monstrous equations? The ones that seem impossible to solve just by looking at them? Well, for those, you need what one of our sources calls a secret weapon, the algebraic method. The beauty of this method is that it turns a tricky chemistry puzzle into a totally straightforward math problem. You just label each compound with a variable, you create a simple equation for each element, you set one variable to 1, and then you just solve. It's a step-by-step recipe that is guaranteed to work, with 0 guesswork. Now, to see just how powerful this is, let's put it to the test on an equation that would be an absolute nightmare to solve by just looking at it. This is where the systematic approach of algebra really shines. And here it is. The source from ChemBuddy calls this one surprisingly hard because the final numbers, the coefficients, are going to be incredibly high. If you tried to guess this one, yeah, you'd be here all day. But with algebra, we can crack it. Okay, step 1, we just assign a variable, A, B, C, D, and E, to stand in for the real coefficients, and just like that, we've officially turned our chemistry problem into a math problem. Step 2 is building our rules. We'll just create one equation for each element. So for example, let's look at phosphorus, P. On the left side, we have 2 of them in that first compound, so that's 2A, plus 4 in the second compound, so that's 4B. And that has to equal the phosphorus on the right side, 1 in D and 1 in E. So our rule for phosphorus is 2A plus 4B equals D plus E. See? We just do that for every single element, and that creates our roadmap. And now for the algebra. I know it looks like a tangled mess, but we just have to find a thread to pull. Looking at our rules, we can see some pretty simple relationships. For iodine, we know 4A equals D. For oxygen, C equals 4E. We can use those as starting points. We just substitute 4A everywhere we see a D in our other equations. By plugging these simpler bits into the more complex ones, the whole puzzle slowly starts to unravel, and we can solve for each variable one by one. After all the math is done, this is what we get. Now, I know what you're thinking. Those aren't whole numbers. And that's perfectly okay. This is the correct ratio. The only thing left to do is to make them all nice, clean integers. We just need to find the smallest number to multiply everything by to get rid of those decimals. And in this case, that magic number is 10. And voila, the final balanced equation. I mean, look at those coefficients. 10, 13, 128. Can you even imagine trying to guess those? It's the perfect proof that we got to this super complex answer not through random chance, but through pure step-by-step logic. Okay, so we can solve these puzzles. That's cool. But why does this skill actually matter outside of a test? Well, balancing equations is the language we use to describe and quantify pretty much everything, from the reactions happening inside our own bodies to massive global environmental processes. Take this quote about ocean acidification. When we write out the balanced equation, CO2 plus H2O goes to H2CO3, we see a perfect 1-to-1-to-1 relationship. For every 1 molecule of carbon dioxide the ocean absorbs, 1 molecule of carbonic acid is created. Balancing the equation is what lets us actually quantify the impact and really understand the scale of the problem. Or think about this equation. This is for cellular respiration. It's the reaction that literally powers most life on Earth. It tells us that for every 1 molecule of glucose we use for energy, we produce exactly 6 molecules of water and 6 molecules of CO2 as waste. It's the precise balanced chemistry of being alive. And this, right here, this is where the hidden power of these ratios becomes crystal clear. This visualizes what happens when we burn gasoline. The balanced equation tells us that for every 2 molecules of octane fuel we burn, we release a whopping 16 molecules of CO2. That's an 8-to-1 output. Understanding that precise balanced ratio is absolutely critical for modeling atmospheric pollution and getting a handle on our environmental footprint. So let's end with this thought. Balancing equations isn't just some boring classroom exercise. It's about deciphering the fundamental rules of how our world works. It is a language that, once you understand it, lets you read the recipes of the entire universe. So, what other secrets can it tell us? Thanks for joining.